Janmey. Jā.
Tas bija HDMI.
Un jums šitais ir priekš pults, lai varētu pārslēgt. Jums nav.
Es varu tepat paliks. Bet jā. Jā, man vajag. Tas cer, ka tas tagad būs. Jā, diemžēl lekcija būs angļu valoda, bet jūs varat, protams, prasīt jautājumus Latvijas, kur es mēģinu atbildēt. Vai vismaz pārtulkot. Okay, so let's start. Anyway, it's great to be back here. I want to tell you some things about the importance of understanding the mechanical properties, not, in addition to the electrical properties and the diffusive properties of tissues. The stiffness of tissues turns out to be a remarkably useful thing, both in understanding how diseases develop and in developing new diagnostic methods. So I want to tell you a little bit about how stiffness, or more accurately, viscoelasticity is measured in a soft tissue, and then hopefully there's time and we'll actually do a little measurement. See if the demonstration works. Okay, so here's what I want to tell you. I want to tell you a little bit about why is stiffness relevant to medicine, not only to clinical medicine, but also to diagnostics. And a lot of this has to do with the complicated structure of tissues, especially soft tissues in the body. And the changes in the structure of the tissue create differences in their mechanical properties, and those mechanical properties aren't simply a consequence of the disease. They will drive the disease or influence how the disease develops. And so measuring stiffness in some way has become a much more common thing to do. And the definition of what stiffness means is kind of a loose, everyday idea, but quantifying exactly what we mean by stiffness is not so simple. It has elements of elasticity and viscosity mixed together in a complex way, and both of those things will influence the way that cells react in a tissue. So I want to spend a few minutes. I hope you've seen some of this simple solid mechanics before, but if not, I'll try to go over it as quickly as possible, and then we'll demonstrate how you, pretty much the principle, but also the practice of how you can measure the elasticity and the viscosity of a tissue. Okay, so what is a tissue? So I have to admit that I've always wondered why in English a tissue is called a tissue. But it comes from the French word tissu, which is related to the verb tisser, which means to weave something. And this isn't an accident. In English, you don't get that impression. To weave is not the same as a tissue, but in French, it's the same word. And in Latvian, it's the same thing too. Audi is the same thing as audīt. Kaut kas, kas ir audīts. And it's also true in German. Gewebe is the word for organ. It's weben is the word for weaving. It's not true in all languages, but in many languages, somewhere in history, people have gotten this idea that a tissue in the body is similar to something that is woven. And so the idea is that these soft tissues are a kind of a weave of protein polymer networks that are surrounding the cells. So the cells in your body are never alone. They're always surrounded by some kind of matrix. And that composite structure of cells inside a matrix is what gives the tissues their mechanical properties. And both of those things can go wrong in a disease. The extracellular matrix can change, and the cells can change by mutation or intoxication or something else. And the way they interact with each other creates the emergent properties of the tissue. And so understanding which one of those changes is responsible for the mechanical features is not possible yet, but both of them contribute. Okay, is that relatively clear? All right, so here's my first little introduction into an oversimplified way of how stiffness in some way is measured. You take a little piece of material and apply a force to it. And that force can either be, let's imagine that you cut a cube of material. You can either apply the force tangentially to the surface of the material and deform it in shear. And this deformation has the feature that it conserves the volume of the material. You cannot squeeze water out of a sponge by shearing it. You could also deform the material by putting the force perpendicularly to the surface, either by compressing it and stretching it, and that in principle can change the volume. And for most simple materials, rubbers and gelatin and things like that, the volume doesn't change very much and the mechanics are fairly simple. So if you measure the resistance to shear deformation, it's similar or calculable from the resistance to uniaxial deformation. For tissues, that turns out to be not true. The composition is much more complicated. The filaments that make them have very different physics from random coil polymers. So there's a kind of a complex physics behind these things, which I'll just ignore, but tell you that that this is basically what you do in all these kinds of measurements. You put a known force on the material, and you measure how much it deforms. And the deformation is usually a unitless kind of parameter called the strain. And if you have a material that is a solid, a perfectly elastic object, if you put a known force on it, you get a constant deformation. Or if you have an apparatus that puts a constant deformation, you get a constant force. And the ratio of the force to the deformation gives you some measure of stiffness. In experiments, the amount of force depends on how the size and shape of the particle of the object you're deforming. So to kind of get rid of that geometric complication and get a real intrinsic material property, there's a little bit of geometry to be done to get real material constants. So rather than talking about forces, the relevant idea is a stress, a force divided by an area, and the strain is a unitless parameter that tells you something about the deformation. The stiffness number that I'm going to show you in the next few slides is always an elastic modulus. It's the ratio of the stress divided by the strain. Okay? Any questions? Is that pretty clear? I'm kind of guessing that many of you have seen this before. Is that true? Yeah, okay, good. So this is about the kind of the zero order method of how stiffness is measured. One assumes that it's an elastic spring-like object. You put a force on it, you see how much it deforms. You don't worry about the time-dependent changes that might happen. And the other thing that's important in biology is that the strains, the deformations that tissues undergo are quite large. When you take a deep breath, you are stretching your lung tissues 10 or 20%. You're stretching them very close to the limit at which they will break. So I don't know if you've ever tried this, but you probably shouldn't. But a normal human cannot take a maximally large breath more than 20 times. If you don't try it now, but if you try to do the biggest breath you can as fast as you can 20 times, you probably will faint. It's a protective mechanism because if you keep stretching the lung, it will be damaged. And this happens on people on respirators. So in biology, we're often pushing things to near their limit. So strains are large, tens of 20%. Every time your heart beats or your aorta expands during a heartbeat, it expands close to where it will break. A little less, but not that far. Okay, all right, so this is the kind of measurement that people have done. And if you do this to a tissue from a normal animal, in this case, it's the aorta of a mouse. Is there a pointer? There is. Which one is the pointer? It's not working. Oh, kind of. Okay, if you do it from the aorta of a mouse, of many mice, these things have a shear modulus of about 2,000 Pascal, measured at about 1 Hertz. And to give you some intuition, if 100 Pascal is about the stiffness of mucus, 10,000 Pascal is the stiffness of gelatin, the gelatin that you eat. So most of our tissues are in that range, somewhere between mucus and somewhere between, well, you know what your own tissues feel like, a few thousand Pascal. So the blood vessel of a mouse is about 2,000 Pascal. And notice how small the variance is. So these are many animals at the same age, the same state of health. But you can change that stiffness a lot by either introducing diseases or just mutations. So in this case, my colleague has made genetically engineered mice that do not make a protein called ApoE. So this is a protein that's involved in atherosclerosis. And these mice will all develop heart disease, even if they have a normal low-fat diet and live a good life. They will all get heart disease and die at a young age. And their aortas are much stiffer. And if you give these animals a drug that doesn't cure the mutation, but just makes the aorta softer again, the animals will all live. They won't get the disease. So stiffness is driving something. All right. The other thing that stiffness is very commonly studied now is in the development of fibrotic diseases or some forms of cancer. So one of the more dramatic examples that's used clinically a lot is to measure the elastic modulus of the liver, often by ultrasound, but by other methods as well. If you can measure the stiffness of the liver, you can learn a lot about the clinical pathway of the patient. And so one of the more obvious changes is a normal liver is somewhat softer than an aorta. It's a few hundred Pascal. But a fibrotic liver can be 10 times stiffer. And the same thing happens with some cancers. This is most dramatically studied in breast cancer and colorectal cancer, but now in a mouse model, as a mouse mammary gland becomes diseased and will become a breast tumor, the elastic modulus changes by a lot, by orders of magnitude. And this is why physical palpation works as a diagnostic test. You can tell the stiffness, you can tell the presence of a growing tumor because at least in some tissues that tumor is stiffer. So you can feel it before you can see any obvious disease traits. Okay, so that has driven a lot of interest in understanding why the breast tissue gets stiffer during cancer development, and also if you could reverse the stiffness, could you slow down the cancer? All right, and I'll show you one example of how effective this stiffness measurement is. So this is a study in Japan where measurement of liver stiffness is a common diagnostic on admission to a hospital for a liver disease. Everyone gets their liver stiffness measured. And these patients have come into the emergency room or whatever, and they get their stiffness, their liver measured, but none of them have cancer. And then the patients are followed for the next, X years to see whether they develop cancer. So the patients that come in for whatever reason and have a soft liver have a very low chance of developing cancer of the liver. The stiffer, every one of these things is a different class of stiffness. The stiffer the liver is, even from a patient that doesn't have cancer when they come in, 5, 6, 7 years later, they have a much bigger risk of getting cancer than if they came in with a soft liver. Why this isn't clear, but it is the most accurate predictor of risk for getting cancer. Liver cancer is one of these cancers where there is not a unique gene that is associated with many cancers. Liver cancer is associated with hundreds of mutations or thousands of mutations. So there's no chemical or genetic test for risk of liver cancer, but stiffness seems to be the best thing there is. Okay, so check on the time. What next? Okay, so I don't want to overstate the case that stiffness changes are not a bad thing. They are a normal part of development. So when your heart develops, in the embryo, the first time there is a muscle cell, a cardiac muscle cell that is contracting in the embryo, it lives in an environment that has approximately the elastic properties of mucus. The cardiac cushion where these first heart cells are born is very, very soft. But the cell is now developing and turning into what looks like a real muscle cell. It's able to contract and beat. It looks like a developing heart. It is a developing heart. But as the animal matures, in the adult heart is 100 times stiffer than the beginning tissue where the heart came from. And you may know this about cardiac cells, that they divide very, very slowly. So this is more true for you than for me, but cardiac cells divide so slowly that most of you, the cells in your heart are exactly the same cell you were born with, or even before you were born. It's the same physical object, but it has reprogrammed itself so that in the adult heart, it can work in a very stiff environment. It's much stronger, it pulls more with more power, but it's still the same object. The genetic program has changed, the proteins have changed, but it has learned how to adapt itself to a new stiff environment as development happens. Okay, and the other example I want to show is that diseases, especially cancers, are not always associated with stiffness changes. And the most prominent example are brain tumors. And I think Professor Sock this afternoon will talk a little bit about how brain and other tumors are measured by magnetic resonance, elastography, and other methods. But one of the discoveries in the brain is that unlike many other kinds of tumors, brain tumors are not stiffer. They're not, depends on what kind, but gliomas, the most kind of deadly and common brain tumor, they are not stiffer than the normal brain tissue. If anything, they're slightly softer. But they are mechanically different. They are mechanically different not because the elastic part is different, but because the viscous part is different. And I think Professor Sock will talk a little bit about that. Okay, so what to do about this stiffness? So a kind of a growing field of biophysics or physical mechanobiology is to do regular in vitro cell biology, which I guess some of you must have done in a lab at some point, but to grow cells in culture, not on glass or plastic, which is kind of a terrible idea. People do it because it's very good for microscopy. You can see through the glass beautifully, the cell looks really nice, but the mechanical environment of a cell on glass is, from a mechanical point of view, extremely stressful. So the transcription profile of cells on glass has very little to do with the cell in the body. And that has led to many problems of understanding things like drug effectiveness. A very common finding is that an anti-cancer drug will be very good at killing cancer cells that are living in a plastic dish, but completely useless if you try to kill a cancer cell in an animal. But you can see when the drugs fail by culturing the cells in a more mechanically realistic environment. So a common thing that is done is to replace growing cells on a piece of glass or plastic, but you put on top of the plastic surface a small hydrogel that has the same elastic properties as the tissue you're trying to study. So, and it's possible, there's many soft materials you can make that span this range from a few hundred Pascal to 10,000s of Pascal, which gives you everything from the stiffness of the brain to the stiffness of a developing muscle. Okay, and then put the cells on top of that and see what happens. And so if you do this with liver cells, you see this beautiful, remarkable change in the morphology of individual cells. So these are cells from the liver called hepatic stellate cells. They are not usually the cell that gives you liver cancer, but they're a cell that reacts to fibrosis by making the environment easier for cancer cells to grow. So in these experiments, these stellate cells, which normally are not very spread, they're relatively small cells, they do a lot of metabolism, but they don't, they're not big, they're not contractile, typically. And if you grow them on a material that is just as soft as a normal liver, they maintain this kind of normal phenotype. They look a little bit brown because one of their jobs is to store fat-soluble vitamins. But if you put the cells on increasingly stiff materials, genetically it's the same cell, the chemical environment is identical. The only thing that's different is how much elastic resistance they feel on the bottom. The cells become fantastically bigger, and they convert their phenotype into the same kind of dangerous phenotype that happens during liver fibrosis and that presumably gives you a risk of developing cancer. And so we've been studying how long you could grow these, and can you now reverse the phenotype back to normal by reversing the stiffness changes. Sometimes you can, sometimes you can't. But it's a very big change. The other kind of photogenic example of stiffness changes in muscle these are heart muscle cells taken from an adult mouse. So these are cells that in the heart has a stiffness of about 5 kilopascal, the adult heart does, and the muscle cell in this heart looks kind of like this. It's a sort of an elongated thing. It has these little stripes on them, which are the actomyosin fibers that do the contraction. And if you culture it on a soft gel with a stiffness, the cells that came from the heart, from the three-dimensional heart, and they were just exploded out of the heart by dissolving everything, the cells, as you take them out of a tissue, become spherical and kind of lose all of their environmental information. And now if you put them down in surfaces, they will still survive and they will do things, but what they do depends very much on how stiff the material is. So if we now take the adult heart cell and put it on a material that is much softer, this is the softness, the stiffness of an embryo, of the embryonic heart where it originally came from, but now it has reprogrammed itself to live in an adult environment. if you put it back in this very soft environment, it can't function properly. It will still stick and it will live, but it won't look like a muscle cell. And in the other extreme, if you put the cells on surfaces that are abnormally stiff, so glass, for example, they make these beautiful cells, and they're nice to study, but they don't have the function of a normal muscle cell. And something that is probably relevant to heart disease is if you put them on materials that are stiffer than normal, but not crazy stiff like glass, but as stiff as an injured heart tissue during a heart attack, for example, that scarred heart has a stiffness that's bigger than the normal heart, and that stiffness itself will cause surviving heart cells to begin to malfunction. Okay, so there's that. But the other thing that's important to point out is that soft tissues in the body, and you probably can test this on yourself, most of our tissues are solids. They maintain their structure. Even if you deform them and let go, they will come back to their original shape. But during the deformation, some of the energy of deformation is elastic and stored, and some of it is dissipated as though it's a viscous thing. Because again, your tissue is 70% water, and as you deform the materials in the tissue, there is a lot of viscous activity. Not terribly much, but quite a lot. And so people have made surveys of hundreds of different tissues, from skeletal muscles to softer tissues to artificial materials, bioengineered materials, and they have measured what I've been showing you, this so-called storage modulus, the elastic part of the stiffness. And here on the y-axis is the viscous part, the part that's dissipative. And there's this, for unknown reasons, there's this kind of master curve that tells you that when you deform soft tissues at about a rate of 1 hertz, or something like our heartbeat, 10% of the energy of deformation is lost to viscosity, and about 90% is stored. So the viscous part is about 10 times as important as the elastic part, but it is still really important for how cells respond. And so we've been trying to understand how to measure this in a relatively convenient way. And the easiest way to think of these kinds of materials that are part viscous and part elastic is to imagine that you have a composite material made out of 2 elements. One is an elastic spring, and the other one is a so-called dashpot. Kas ir dashpots latviski? Vai ir tāds vārds? Vienkārši kaut kāds, jā.
Kāds pots? Dash vai mash?
Dashpot. Tas ir, piemēram,
Kaut kāds pots.
Jā, tā, piemēram, mašīnā, kur atspēr ir, tā šakabsorbers ir pus atspēr un pus kaut kāds šķidrums. Yeah, amortizators. Yeah, okay, perfect. Okay, so that's the idea. You're part spring, part viscous dissipation. And those 2 elements are in parallel. If they weren't, if they were in series, that when you pull on your tissues, they would keep pulling. But they're in parallel, so you will elastically recover, but some of the work is dissipated. All right, and it's important to understand both of those elements. And partly the reason it's important, or one illustration of why it's important, comes again from cancer measurements. So here again is a study of breast tumors in the mouse. I told you before that, at least in some kinds of tumors, the the tumor is much stiffer than the normal tissue. But it's very important for surgeons, if they take out a tissue or they take out a tumor, it's obvious from histology where the tumor, where the cancer cells are. But in the boundary between the tumor and the normal tissue are cancer cells that haven't really developed into something that is histologically obviously malignant. So the surgeon needs to take out the right amount of material in between the clear tumor and the normal tissue and needs to know how far to cut. And it's difficult to tell that just by doing regular histology. But it turns out that if you can measure not the elastic modulus, if you measure the elastic part, there's a little bit of difference between the marginal area and the normal tissue. But if you look at the viscous part, the dissipative part, there's a much bigger difference. So for example, if you put a deformation, if you deform a normal tissue in blue, when you deform a normal tissue, if you just push on it, the resisting force decays slowly over time, over 10 or 15 seconds. And that's because of this viscous part of the mechanics of the tissue. But the tumor is almost completely solid. It's stiffer, but it's also more elastic, less dissipative. But the area in between is now clearly less dissipative than the normal tissue. So you can easily tell the difference between the boundary and the normal tissue much more easily if you can measure this viscosity than if you try to determine it just from elastic measurements. And I think Professor Sock has some things to say about that as well. Pag-check likes, Philip Pullets. Oh, 10 minutes, okay, super. All right, so let's try to measure this. Okay, so I told you before, there are these various ways to measure it. You can either push on a sample or deform it in shear. And what we're going to do with this torsion pendulum is deform things in shear. And all right, so I'm just going to skip over this. I think you probably know this already. So the principle of what we're going to do is based on the harmonic oscillator. So raise your hand if you have. You must have had this in class, yeah? Okay, fantastic. Okay, good. So relatively little and relatively simple mechanics. Okay, so imagine you have something that's purely elastic, just a spring on below which you attach a weight. And you pull on the weight and you watch the spring oscillate. Okay, so just to remind you of what you may or may not have liked to study, if you write down a force balance, this little mass is accelerating. So the force on the thing is mass times acceleration on the object, and it's resisted by a spring constant, K, that the force that the spring is resisting the motion of the mass is proportional to how much that mass is deformed, right? So you have this sort of fairly simple equation that you can solve pretty easily. You can just reformulate it to mass times d squared x dt squared equals minus kx. If you solve that equation, it's just a sinusoidal function with some amplitude. And as long as it's purely elastic, the thing will oscillate eternally. And the useful thing about this is that the frequency of the oscillation gives you a way to measure the spring constant, K. The frequency of the oscillation is the square root of the spring constant divided by the mass. The mass you can measure, the mass you know, the spring constant typically you don't know but want to measure. So this is the thing that we're going to be interested in measuring. This is the elastic modulus of the tissue to some extent. Okay, so that's the idea. We're going to use something like this to measure the stiffness of a tissue or any soft material. But the problem is that these tissues aren't perfectly elastic. They're also viscous. And we'd like to know the viscous part too. And so now you imagine what happens if you put a harmonic oscillator in a little viscous bath. So this thing, the cartoon isn't showing you this, but every time it dips into the viscous bath, it will lose some amplitude of oscillation. So again, if you write a force balance down for this, you have a slightly more complicated equation. The force, again, is mass times acceleration. It's resisted by the spring constant times the distance that it moves. But now there's a new term, a kind of a dissipation term, the importance of which depends on the rate at which the, dx dt, the velocity with which the object moves. So you can, again, solve this equation, or you could reformulate the equation and introduce a variable c, which is the kind of dissipation, the kind of typical viscosity contribution, divided by some fraction, or some function of the spring constant. And I told you before that most soft tissues are 90% elastic, 10% viscous. So if you want to solve this equation, the solution depends on how big this term is, or how big C is compared to K, right? The more elastic it is, the more it's going to look like an oscillatory function. If the dissipative part is too big, it won't oscillate anymore, you'll just get an exponential decay. But for us, we can make this assumption for the soft tissue that the dissipation term is very small compared to the elastic term. Okay, so you can, if you solve that, then you get a very pleasant kind of formulation where the motion of the little weight is still a sinusoidal function with a frequency from which you can calculate a elastic stiffness, but now it's modulated by an exponentially decaying term from which you can calculate a dissipative part or an effective viscosity. Okay? I'm guessing that this is review for most of you. All right, so now we're going to try this. But we're going to try this in a slightly variant way. Instead of a weight bouncing into something, we're going to make a little pendulum. We're going to make a little crossbar pendulum and put in something in the middle. Piece of liver, piece of brain, in our case it's a piece of, well, it's not a piece of tofu for this, but it will be a small, sample of some elastic material. Okay, but that's the thing. You cut a piece of material in it. As long as you know the size and shape of the material, you can relate the spring constant, measurement to a real material shear modulus. All right. And so instead of bouncing up and down, we're going to put a torque on the material and have it bounce back and forth. And the important things to know is that the so-called mass, or the mass in the early harmonic oscillator, is replaced by the moment of inertia of the pendulum, which is just a geometric thing. So that's something we know we'll be able to calculate. And the spring constant and this damping constant are now both hidden in the material that we're going to measure. So both the elastic resistance and the dissipation are sitting in this material that we're measuring, and we're going to introduce a resonance to the pendulum and calculate the frequency. So the frequency will give us a measure of the shear modulus, and the damping constant will give us a measure of the dissipation. All right, that's the idea. All right, let's see if this works. So basically you do exactly the same thing. You set up a kind of a force balance, but now instead of a linear force, we have a torque. Instead of a mass, we have a moment of inertia. And instead of a velocity of motion, we have the rate of change of the angular displacement of the pendulum. Mathematically, arithmetically, it's exactly the same thing that for the harmonic oscillator. Okay, and sorry, and from this we can calculate a frequency. The frequency is the undamped frequency modulated by some kind of damping thing. It's a tiny term, so you can sort of forget it. And the decay of the amplitudes will give us this kind of friction constant, which will give us a so-called loss modulus. Okay, so here's one example taken from an undergraduate in our lab a few years ago who was measuring tofu. So this is a slightly different pendulum from what I'm going to show you, but it's the same idea. You make a home-built little pendulum, you put a piece of tofu in between a stationary plate and this little oscillating pendulum, and you give the pendulum a little poke, and it oscillates. And the big advantage of these oscillating pendulum things is that you don't have to measure the force yourself directly. In most instruments, they're expensive and complicated because you have to both measure deformation accurately and you have to measure force or torque accurately. Here you don't have to measure the force, you just have to start the motion, and the force is all provided from the material you're measuring. All you need to do is measure the resonance frequency. All right, let's see if this works. Questo policzek, this much lasers, pretty nice, yes. All right, let me see if I can get this to work. So here I have a little pendulum set up that's sitting on a piece of, or maybe, okay, cik laiks ir, vēl 5 minūtes, 10? Labi, nu tad pamēģināsim varu šito, ja varat. So, oh, you can see it on the screen, perfect. Okay, great, okay. All right, so when I set it up before, so careful over there if you're tall, because I think the laser it's going to shine or be reflected just where it says Latvijas Universitāte, but I'm going to try to do it. So here is a little torsion pendulum, the moment of inertia of which I know, and it's now sitting on a piece of some elastic material. And okay, now okay. Oh, sorry, it's right on your head. Let me do something here. All right, so I'm going to give the little pendulum a push, and I can give you this as a homework problem because I know the moment of inertia and I know the size and shape of the sample. So let's see if this oscillates. Yeah. Okay, so all you have to do is time the oscillations, and from that you get the shear modulus. And if we had taped, well, actually you can just film it with a cell phone camera now, and look at the damping of the oscillation. So this thing is a fairly elastic thing, so it will, when it resonates, it will make about 10 oscillations before it completely dies. And so, and this is exactly the same principle that actual instruments use to measure this. As long as you can have a material that is slightly under damped and that resonates, you just give it a little impulse, and measuring the frequency is pretty easy. I'm guessing the frequency is something like 0.5 hertz. 2 hertz, and yeah, it's close to 1 hertz, and the damping is relatively small. So probably there are 10 oscillations until you lose an order of magnitude of motion. So from that you can calculate a damping constant. But as I mentioned, probably it will turn out that the damping is 10% as big as the elastic part, and the only question is how to relate the frequency of the oscillation to a shear modulus. Okay, I think that's it. Running out of time.